Hi, I think about the 3x plus 1 problem all the time, and I think about it differently than anyone else I know, anything I've seen online, and anything any mathematician has considered. So I've come to the conclusion that my thinking is along the lines that the problem is solved or explained by a Turing machine, and I'm going to explain why, but that's not the main subject really. It's just a model. So moving on, this is really where I got the idea that it's like a Turing machine, because here I've put a lot of sequences, some sequences together in a list consecutively, starting with the odd integers on the left column, and then their first odd output in the next column. And I realized that what's enclosed in the rectangle is actually like the tape in a Turing machine, which can compute anything by looking at the input and then performing an instruction on it using the head of the machine, which moves up and down, or rather it moves the tape up and down. And just to back up for a second, so I don't think mathematicians realize that considering individual sequences is very misleading, and it's far more enlightening to view sequences together en masse as a structure. So that's the underlying theme of what I'm going to be talking about. So there's an implicate order to this structure, and it's defined by three simple congruence classes, which I'm going to label A, B, and C. And actually these are rather like the letters of a finite state machine or deterministic finite state machine. So I have three states which are congruences, and these produce three outputs which are transitions. So just to keep that in mind, let's press on with the idea of A, B, and C, and they're actually called letters in finite state machines. So congruence A is n plus 1 congruency mod 4. That just means that the odd number plus 1 is evenly divisible by 4. So there's a series 3, 7, 11, 15, 19, 23, and so on, which goes on to infinity. Congruence B is an odd n minus 1, congruent 0 mod 8, which means it's evenly divisible by 8, and this series is 1, 9, 17, 25, 33, 41, and so on. You might be wondering why 1 is congruent 0 mod 8. Well, remember, n minus 1, or 1 minus 1 is going to be 0. So that's why. Whereas n plus 1 would make it 2, and that definitely would not be congruent 4. So 0 is congruent with any 0 with any number. Congruent C is n minus 1 congruent 0 mod 4. So that the difference between that and the first one is this is n minus 1. And remember, n is always odd. And so this sequence is 5, 13, 21, 29, 37, 45, and so on. All of these series, really better to call them series and sequences, go on indefinitely to infinity. Now, what's interesting here is if we take the left and right columns from that first table when I was talking about the Turing tape, we see on the left side, on the input side, this repeating pattern, CABA, 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 without variation. And we notice that A is twice as frequent as C and B, so the ratio is 2 to 1 to 1. In the output column, we see a slightly different, we see a pattern, but it's a little bit more complicated. It actually repeats itself every 16 units, a 16-unit cycle. So I'll just show that further on. It may be more understandable. And then from that point out, everything gets jumbled. A, B, and C get jumbled, and for reasons which I will attempt to explain. But that's the beauty of just sticking with one input, one output, because everything is explained here. And so, for example, I don't know if you're familiar with the sequence that begins with 27. That's one of the long ones, and it's one of those that impresses people unfamiliar with the conjecture. So 27, and we're only considering odd numbers, 27 goes to 41. And then you can imagine the tape being moved up and the head reading, 41 goes to 31. And then you can imagine the tape going down and it's 31 goes to 47. So that's really why it's a Turing machine. Very, very simple indeed. And the question is, does it halt? So there's this related conjecture or question, which has been proven undecidable, that does a Turing machine halt? It's called the halting problem. And it depends on the inputs. And it's really, until it happens, it's unknown, it's undecidable. But if the Collatz conjecture is proved true, that means that this Turing machine halts on 1, always on 1. And so it's an equivalent way to express the problem. Here, I'm looking at those 3 congruence classes and seeing how they shake out in the number line. And you see that the lower one is C, the middle one is B, and the upper one is A. And the one takeaway from this, I think, is that Congruency actually is a set of all the natural numbers without interruption. It's a set of all the natural numbers, and each of these numbers will be repeated as an A or a B congruence, but that doesn't produce circularity or looping, which you might suppose at first. So it actually has nothing to do with that. The only thing it has to do with is branching. And we'll get to that, I think, in a little bit. So next. Here we look at input-output congruences in a little bit more detail, and want to make you aware that the output congruences are not a mirror of the input congruences. Remember I talked about this 16-unit repeating cycle. Well, here you can see it in the lower half of this table, so that 31 is congruence A, and 47, the output, happens to be congruence A as well, and 33 is congruence B, and 25 happens to be congruence B as well. But then we get to 35, and that's congruence A, and the output is congruence C. And then the next one is input 37, which is congruence C, and the output is congruence B. So the congruence is switching as the numbers transition from input to output. And the ratios are as shown above, where the most common case is A to A, and then you have cases, this is the 16-unit cycle, so A to A is a quarter of them, and then A to B is 1/8, A to C is 1/8, B to A is 1/8, C to A is 1/8, and the remaining quarter are B to B, B to C, C to B, and C to C. These never change. Okay, so they're significant from the point of view of our Turing tape, but beyond that, they're not affecting the sequences in any predictable fashion. But that's again why the Turing tape analogy is so powerful. So here I have a function that describes exactly what I've been talking about. And I explain those three congruences on the right side of the function. And now I'm showing also the three operations that are associated with them. So the respective operations are for A, n plus 1 times 1.5 minus n. And this keeps a whole number. So we get an even number, n plus 1, and then we're able to multiply that by 1.5, and then we subtract 1 and get an odd number. And then with B and C, we're subtracting 1, and in one case we're multiplying by 0.75 and adding 1, and the other one we're just multiplying by a quarter. And so we can see that the growth operation, the only congruence that is resulting in a growth operation is A. B is reducing the size of the step sequence number by 3/4, and C is reducing it by a quarter. Let's move on. So this is really easy to understand. The inputs, going back to the series which I introduced at the beginning, are A, B, and C. They're the columns in the input side, and then on the output side I'm not showing the congruences the way I did a couple of slides ago, because it's actually easier to understand what's going on if it just reflects the input congruences. So for example, if you look at the C column for input, you'll see that the differences are always 8, 5 to 13, 13 to 21, 21 to 29. However, it turns out if you divide 5 minus 1 by 4, you get 1. 13 minus 1 by 4, you get 3. 21 minus 1, you get 4 plus 1, 5. So what I'm trying to say is that every odd integer can be an output of C. This is important. This is what makes congruency important. And I'll come back to this in a few more slides. I'm going to stop because I'm tired and you're probably bored. And I'm going to pick this up with part 2, and probably there'll be a part 3 as well. Can't be sure yet. So hang in there, and I'll see you in a bit.